Hey everybody, this is Larry. This is day 8 of the Leetcode Daily Challenge. I believe, yeah. Hit the like button, hit the subscribe button, join me on Discord. Let me know what you think about today's farm. And of course, there's going to be week 2 after that, so definitely check that out as well. Today's farm is going to be 133 clone graph. I feel like we did this very recently, right? Or let me, like Oh no! I think the one that we did recently was a premium prom with like a random extra node, I guess. But it's still gonna, and I think that was like 2-3 weeks ago, maybe something like that. But I don't know. Time really flies. Okay, fine. I'll take a look at today's farm. I mean, I think this one is just way. The formulation, the problem statement is pretty straightforward, right? It's just given a deep copy of just given a graph, return a deep copy of it. And in this case, instead of I think that one was maybe a tree or linked list, I don't remember, but you have a list of neighbors instead. And the hard part about this is that yeah, you can there are a lot of ways to kind of do this. You know, you have to be a little bit careful. I think the way that I would think about it though is kind of separate out the construction of the nodes and separate out the construction of the nodes and then the construction of the lists, right? The way that I have it, the way that I usually do it, and I don't think I explained it as well last time because I had some very good questions in the comments previously. But the way that I do it is having a lookup table, and then now for this node, well, how they're giving us the list? You're just giving like one node. So I'm just looking at input. I guess you're just giving one node and not an adjacency list. Okay, fine. I mean, that's fine either way. But the idea here is, okay, so then maybe you do a recursive creation, and for n is equal to 100 is way easy, or like in terms of complexity, so you wouldn't have to worry about it. But yeah, and then you have a node, right? And then basically, the way that I would think about it is this function returns a new version of this node, right? Returns a new version of this node, right? And here, let's just say, I don't know, new node is equal to fetch node, right? And then maybe you have a fetch function that looks like this for a node. And then basically if lookup, or if node is in lookup, return lookup of node. Maybe I'll write this a little bit differently. If this is not in it, then lookup of node is equal to new node of value of node.value. We don't have to worry about the neighbors for this part. But yeah, and I've gotten some questions about previously about why this works, and I don't think I kind of just skipped over it, to be honest, the last time I did this, because I don't know. I mean, I think it just it's just an experience thing, right? And I kind of sometimes forget people might not have the experience, and which is that you assume that the key in a Python hash table or lookup table or dictionary is going to be immutable, right? But why is a node which you can make random changes? Why can you use this as a key to this lookup table? Well, it turns out that for most things, it's not the content of the node that matters. It's the address of the node, because the address of the node is the immutable part. So basically what I'm saying, and there are other ways to write this, you can even think about it, but basically this is just looking up the address of node, or in some languages you may call them pointer, you can call them address, and all these stuff. In Python it is going to be the I think it's called an object ID or something like this. Or maybe not an object ID, but something ID, I forget. But that ID is the core for it. And you can even do it that way if you want to be more explicit, right? You can just do something like this, and that will get you the the Python address of the node, and because we want to map exactly one node object with this second node object, this should be okay, because if we get a different address, then it is effectively a different input, right? So basically that's what we're trying to do here. So okay, and then now trying to figure out how to do this in a clean way. I mean, maybe you can do something like for v in node.neighbors. New node.neighbors dot append construct of v, but this doesn't quite work yet. I'm trying to think real quick. This doesn't work yet because now you have like infinite recursion is why. I mean, you could even see this yourself if you just had done something like this. Right, it'll give you a maximum recursion thing, and the reason is because it's going back and forth, right? I mean, yeah, you don't really need that many inputs there. Yeah, I mean, I was just trying to think. What is the best way to handle this? I mean, there are a lot of ways to handle it, but I'm just trying to think about a clean, easy way. I guess the other one that we had was a tree or a linked list, so then it was effectively a DAG, maybe a doubly linked list. I don't remember, but either way, it was effectively a DAG, which won't have this issue. I did kind of expected this, and you can kind of. I guess the other way we could do that is do a fetch instead. So then now this won't be an infinite loop, but also won't be also won't be correct because it's not. Oh, this could be none. Wait, what? That's weird. Why can't this be none? I guess this. If node is none. Okay. Well, I mean, that's just a silly case, really. Right? I mean, that's just like useless waste of time. But yeah, as I was saying, you don't really return the right graph, so this is going to be wrong. But I think maybe the slightly better. I mean, and you could do it in both ways. It doesn't really matter. But yeah, I mean, I guess it doesn't really matter. You could. I was thinking you could do it at a breadth first search or a depth first search. Either one is fine with this construct, but I'm just going to do it recursively and then just have a done thing, right? And the same thing with done applies here, which is that if node isn't done, we return done of node, maybe. I don't know, right? And then now, after all this, we can do it one more time. Well, after this, we can do it one more time and then just construct v maybe. Does it still go? Oh, so oh, whoops, that's why. Oops, that was a silly typo. I was like, I think the logic is okay, but let's give it some minutes, see if maybe I still made a mistake. I look okay. 1103 streak. This is going to be a linear time, linear space. Can't get around either of those really. Linear space is here, but that's also the size of the output, so you really can't change anything about it. Linear time, because for each node, you only call this one thing once. Well, and just to be clear, linear time and space in this case, linear time and space in this case is actually v plus y, where v is the number of vertices, number of nodes, and y is the number of edges, right? Because you have to process each edge, twice, I guess, maybe 4 times in both directions or something like this. And yeah, but it's still gonna be O of y, and then O of v, because you only call this for each node once or twice, maybe, but the second time will be, pretty early. So yeah, that's all I have for this one. I'm curious how did I did it in the past. Man, past Larry did have this much cleaner, but I guess this is the same idea. I just kind of added a new thing for fetch. Yeah, I guess that's what I did. This one is way more complicated. Oh, this one, I was kind of maybe talking about it, but I don't know. Yeah. And then this, that time I did a buffer search, and then also cached the thing explicitly. Yeah. They all do the same thing really. So yeah, let me know what you think. Yeah. Hope y'all have a great weekend. Stay good, stay healthy to good mental health. Have a great long weekend if you're in a country that's has it off or celebrate it. But yeah, stay good, stay healthy to good mental health. I'll see y'all later and take care. Bye bye.